Welcome to DA classes. Today we're going to learn about the conservation of momentum, a fundamental principle in physics that helps us understand how objects interact when they collide. Let's start with the basics. Momentum is defined as the product of an object's mass and its velocity. It's represented by the letter P and mathematically written as P equals m times v, where m is the mass and v is the velocity. Since velocity is a vector quantity, momentum is also a vector quantity. Now, let's understand the conservation of momentum principle. The law states that in an isolated system, where no external forces act, the total momentum before an interaction equals the total momentum after the interaction. Mathematically, we can write this as the sum of initial momenta equals the sum of final momenta. Let's derive the conservation of momentum equation for a one-dimensional collision. Imagine we have two objects with masses m1 and m2 moving with initial velocities v1i and v2i. After they collide, their velocities change to v1f and v2f. According to the conservation of momentum, we can write m1 times v1i plus m2 times v2i equals m1 times v1f plus m2 times v2f. Let's visualize this with a simple animation of two balls colliding in one dimension. Now, let's extend this to two dimensions. In two dimensions, we need to consider the x and y components of momentum separately. For a collision between two objects in two dimensions, we have m1 times v1 ix plus m2 times v2 ix equals m1 times v1 fx plus m2 times v2 fx for the x dimension. And similarly for the y dimension, m1 times v1 iy plus m2 times v2 y equals m1 times v1 fy plus m2 times v2 fy. Let's visualize a two-dimensional collision, like billiard balls colliding. Now, let's discuss the types of collisions. First, we have elastic collisions, where both momentum and kinetic energy are conserved. Think of billiard balls or perfectly bouncy balls. For elastic collisions, we have two equations: conservation of momentum, m1v1i plus m2v2i equals m1v1f plus m2v2f, conservation of kinetic energy, 1/2 m1v1i squared plus 1/2 m2v2i squared equals 1/2 m1v1f squared plus 1/2 m2v2f squared. In an elastic collision, objects bounce off each other, transferring both momentum and kinetic energy. Next, let's look at inelastic collisions. In inelastic collisions, momentum is conserved, but kinetic energy is not. Some energy is converted into heat, sound, or deformation. Examples include cars colliding or clay balls sticking together. For inelastic collisions, we only have one equation: m1 times v1i plus m2 times v2i equals m1 plus m2 times v final. The most extreme case is a perfectly inelastic collision, where the objects stick together after collision. Let's visualize a perfectly inelastic collision. Now, let's move to a related topic: the equilibrium of a particle. A particle is in equilibrium when the net force acting on it is zero. This means that all the forces balance out. Mathematically, we can write this as the sum of all forces equals zero. For a particle to be in equilibrium, both of these conditions must be met: the sum of all forces in the x direction equals zero, and the sum of all forces in the y direction equals zero. Let's look at an example of a particle in equilibrium. Let's look at some real-world applications of these principles. The conservation of momentum is used in rocket propulsion. As the rocket expels gas backward, the rocket moves forward. In sports like billiards or bowling, understanding elastic and inelastic collisions helps players make better shots. Equilibrium principles are used in structural engineering to ensure buildings remain stable. To summarize what we've learned today, momentum is defined as the product of mass and velocity. The conservation of momentum principle states that in an isolated system, the total momentum before an interaction equals the total momentum after. In elastic collisions, both momentum and kinetic energy are conserved. In inelastic collisions, only momentum is conserved, with some kinetic energy converted to other forms. A particle is in equilibrium when all forces acting on it balance out, resulting in zero net force. Thank you for watching this DA classes video. If you enjoyed this lesson and found it helpful, please like the video and subscribe to our channel for more educational content.